Good evening, everyone. Welcome back to our weekly webinar series on quantum algorithms using Qniverse. So last week we had with us Dr. Manpreet Singh, who taught us variational quantum eigensolver algorithms. And we conducted a survey during last week regarding the timings of the webinar series. And since many of you had requested for the late evening webinar so that you can all attend post your day-to-day activities. So we have scheduled this webinar and successive webinars at 7 o'clock every Wednesday, so that it will all be helpful for you to attend the webinars. Right. Okay. This week we have with us Dr. Divyansh Shrimali. He's a project engineer at C-DAC Bangalore. He has got his PhD in quantum information and computation from HRI Institute, Prayagraj. Okay. He is a researcher and in quantum information and computing with academic foundation from NISER Bhubaneswar, which is he has done an integrated MSc and a PhD from HRI Prayagraj under Professor Arun Kumar Pati. His doctoral work focused on entanglement theory and quantum speed limits, leading to several publications in Physical Review. At C-DAC Bangalore, he is engaged in developing hybrid quantum algorithms, exploring applications of variational methods, and designing novel approaches for optimization and molecular simulation. So this week, Dr. Divyansh will walk through us on superdense coding and teleportation. Over to you, Divyansh.
Okay, thank you, sir. So I will just share my screen. Right. Yeah. I hope my screen is visible.
Yes.
Yes. Okay. So good evening, everyone. My name is Divyansh, and I thank Santosh sir for introducing me. So this evening, I would be talking about quantum teleportation and superdense coding mostly. So let's begin. So this is the outline of my talk. First, I will begin with the motivation, why we need certain protocols like this, and what are the fundamentals which would help us to uh, which are like the foundation because of which these protocols emerge, which is essentially entanglement. So I would be briefly discussing what that is, how entanglement is generated, and then I would be delving into the detailed mathematical analysis of teleportation protocol. Then I would be switching to superdense coding. Then I would be bringing out some connections between these, and then my aim would also be to demonstrate how superdense coding and teleportation is implemented on actual quantum circuits using our proprietary software, that is Qniverse. So let's first come to motivation. So as I wrote in my first line, communication is central to both classical as well as quantum information theory. So classically, we know that if you want to communicate, if somebody wants to send a message from point A to point B, classically there are limitations. Like uh, the limitations are with respect to somebody tampering with the data and ultimately decrypting it. There is no guarantee by any classical protocol that would tell us that this can be made arbitrarily precise, arbitrarily secure. But then we have the realm of quantum mechanics, which gives us certain resources, certain correlations, which are not something that can be simulated via classical means, and it leads us to thinking whether we can make use of these kind of quantum resources to actually make our communication protocol very secure from any sort of tampering whatsoever. So we would be looking with that intention in mind. People thought about how quantum resources can be used to make our communication protocols arbitrarily secure. And of course, entanglement as a quantum correlation came for our rescue. There was another limitation which was about the channel capacities. So classically, what we can do best with one bit of classical communication is we can only pack at most one bit equivalent of information in it. We cannot we cannot encode more than one bits of information through any classical means whatsoever. So uh, can we by invoking quantum mechanics, can we make it a bit better? Can we improve upon it? So those two aspects actually motivated us to look into or explore rather the arenas in which ultimately these two protocols emerged. So basically, teleportation is all about sending an unknown quantum state from point A to point B. And superdense coding is about sending classical bits with as few qubits as possible. So there's one more thing that I would like to mention, that apart from a fun mathematical exercise, it actually also led to the development of important ideas. There were seminal papers written by Grottesman and Chuang in which they explored and they proved that using teleportation, you can actually make better uh, error correcting codes, better fault tolerant quantum computing. So apart from just sending information from one point to the other, it has actual implications and making our the quantum hardware more versatile. So with that motivation in mind, let's delve into uh, some of the basics of quantum mechanics that are essential here. I will be describing about qubits here to start with. So a qubit is a superposition of 0 and 1 kit. But when I write 0 and 1, these are essentially classical in nature. But when I'm talking about the superposition, when we have a state like alpha 0 plus beta 1, so that essentially means that we are dealing with a superposition, and that means that when we perform our act of measurement, then this state will collapse to either one of these two classical bits. Before the act of measurement, we don't know that to what classical bit it will collapse to. So that goes into the essence of quantum mechanics. So these alphas and betas, what they mean is that if you have a significant amount of copies of this particular state psi, and you perform your measurement repeatedly on each of these copies, then then there would emerge a particular pattern in which you would be saying, okay, these many times I'm getting my 0, these many times I'm getting my 1. So that probabilistic outcome is something that hinges upon the coefficients that are alpha and beta. So whenever we perform a measurement on our superposed state alpha 0 plus beta 1, that doesn't mean that we would be getting a real value between 0 and 1, but we would be getting either 0 or 1, and we don't know a priori before the act of measurement to which classical bit it will fall to. This is very essential to understand because this creates all the difference there is between classical computing and quantum computing. So we usually represent our pure state, that is alpha 0 plus beta 1, on a Bloch sphere. So you see Bloch sphere on the right hand side, it, its surface is the space of all the pure states, where all the pure states live. Just inside the surface, the volumetric part is where all the mixed states live. So when somebody says that a pure state is there that is given to you, that essentially means that now if you know that particular pure state, you know everything about the system. But if somebody is sending you a mixed state, that means that there is a classical mixture, there is a statistical mixture of several pure states. And in that way, you may not know everything about the system. So usually when we deal with noises, we are actually dealing with mixed states. And for noiseless kind of circuits and where perfect gate implementations are there on the circuit, we remain with the regime of pure states. and that's where we are going to uh, uh, contain ourselves in during both of these protocols. So as I mentioned, measurement collapses the state to either 0 or 1. Now from one qubit state you can go to multi-qubit state. So you combine your qubit states via tensor products. So let's suppose you had your one qubit state as psi and another one qubit state as phi. Then when you perform your tensor product, you actually get a two qubit state. And similarly, you can do multiple tensor products like this with qubits, and you will get those many like n qubit states as a result of that. If you think about two qubit state, if we remain in that arena of two qubit state, the basis states are represented by the 0001, 10, and 11 kits. These are basis states because these are the vectors which span the Hilbert space of a two qubit state. And for any kind of quantum correlation, we need some interaction. Now, interaction cannot be with just one qubit, so you need at least two qubit. So anything beyond one qubit would give rise to correlations, and those are the correlations that are something that we will make use of in our quantum computing. Now, to perform any correlation, for any correlation to arise, for an interaction to arise, we make use of something called as quantum gates on a circuit. Now, it is essential to mention the difference between classical and quantum gates. In classical world, classical circuits, we deal with well-known gates like AND or NOT, and there are many other gates like that. So these gates essentially are non-reversible in nature. So what do I mean by that? You all have studied about set theory, functions, relations. So whenever you have one-to-one mapping or many-to-one mapping, that kind of one-to-one mapping and one-to-many mapping, that kind of mapping is always reversible. So if you have your Y data sets, you can go back to your X data sets. But when you have a many to one kind of mapping, then the reversibility comes under question. Then the map for that kind of an operation is not invertible. For quantum mechanics, we deal with unitary operations. All the unitary operations are invertible. So we essentially need those kind of states, those kind of gates, which are invertible in nature. And that's why we have to make use of poly XYZ gates, Hadamard gate, and the other gates that you see on the right hand side. So these are essentially, apart from the Toffoli gate, these are essentially the universal set of gates that we make use of in our circuit, and we can make a composition out of them, and we can like perform complex calculations, perform complex computations. So basically, whenever somebody is talking about a quantum circuit, they mean a sequence of these reversible operations. So because each of these operations are essentially matrices by themselves, so basically a quantum circuit is a big matrix that is getting multiplied to the vector on the left hand side, and it's resulting into a vector on the right hand side. So any computation that we would like to perform can be built from the universal set of the gates that are in front of you. For example, I have mentioned uh, but I've added a picture of this particular simple quantum circuit. So what is happening here? We have two qubits, Q0 and Q1. On Q0, we apply our Hadamard operation, and the next operation is on both of them, Q0 and Q1, in such a way that Q0 is our control and Q1 is our target. So when we perform this kind of operation, we generate something called as entangled states. On the left hand side, we have a separable state. On the right hand side of the circuit, we get an entangled state. Now, entanglement is a unique resource in quantum computing or quantum information. So entangled states, just like we had in our two qubit scenario, we had those 0001, 1011 computational states. For entangled states, we have the basis which we call as Bell states. So they are usually like denoted by phi plus minus and psi plus minus states. And on the right hand side is the circuit for that. So the first circuit that you see is the circuit that I just showed before also, and it generates the first Bell state that we are very much used to. It's like 0 0 plus 1 1 by root 2, and subsequently the other three circuits generate the other Bell states that are also unitarily connected to the first state. So what is the relevance of these states? So the entanglement that is shared between two qubits that acts as a resource for our protocols. So whenever somebody talks about quantum advantage, somebody talks about some gain because of quantum regime, they actually make use of this kind of resources, and entanglement is one of the essential resource that we make use of. So basically, entanglement is like a correlation between qubits, and entanglement links qubits instantly. So we'll use this link as a quantum channel, and through this we will actually perform our, or rather, uh, discuss our protocols. So teleportation and superdense coding are essentially a byproduct of this entanglement as a resource. So let's discuss about teleportation problem. So in teleportation, Alice is interested to send an unknown qubit Psi to Bob. By unknown state Psi, what I mean is that if you have a state like alpha 0 plus beta 1, alpha and beta coefficients are unknown to Alice. Somebody has given her this particular qubit as a package, which her task is to send this package to Bob without knowing the state. And she cannot know the state, let's say. Now, the problem with this particular state is that direct act of measurement actually would destroy this particular state. So once, if she performs any kind of measurement on this particular state, she would destroy it, and then there would be no question of sending it to Bob. There is a seminal property or limitation in quantum mechanics, which says that there is no unitary operation. And to tell you, on quantum circuits, all the gates that we implement are all unitary in nature or all reversible in nature. So quantum mechanics through unitary operations do not allow us to copy any unknown state. If you know the state, then you can copy, but if you don't know the state, there is no unitary operation or unitary machine that would be able to copy this particular state. So even if Alice, let's say, has some partial information about the state, and even if she communicates this partial information to Bob, he will not be able to create this state. So no cloning theorem actually limits us in this regime, in this protocol of communication. So is there any way around this? Can we make use of entanglement? Can we make use of some of the classical bits to actually do the task for Alice? So that is the problem of teleportation. Now let's talk about classical limitation. For the same problem of sending a general state like Psi. Okay? So let's say we would like to begin with a certain easement of the restriction. Let's ease the restriction a bit, and let's say that suppose somebody who is giving the task to Alice to send the state to Bob. Let's say that person tells the entire information about the state Psi. That meaning that person is telling Alice about the entire information about alpha and beta. Now, it's imperative, it's important to know that to specify the coefficients to arbitrary accuracy, arbitrary accuracy as in these alphas and betas are normalized in such a way that alpha square plus beta square is equal to 1. So let's say these are some decimal numbers, and in case these are decimal numbers which are non-recurring, non-truncating kind of irrational numbers, then to signify this particular number, you might be required to need a lot many classical bits to actually tell this information to Bob. So if we want to know the entire expansion of these alphas and betas, we might in principle require infinite amount of classical information. So mind you, we are just talking about one qubit state here, alpha 0 to beta 1. This is general state. Now, even this particular state, owing to the form of alphas and betas, can need infinite number of classical bits to encode the information of this particular qubit. Now, this makes the task even more difficult. So this was when we knew the state, right? Now, our task, which was original task, was to pass on a state which was unknown. So it's even more difficult a task. Now, what if I tell you that by making use of quantum resource based protocol, we can accomplish this task by sending just two classical bits. For an arbitrary state psi, alpha 0 by beta 1, where alpha and beta can be arbitrarily complex and they can make use of infinite number of classical bits to encode the information of alpha and beta to be sent to Bob, we are doing this task by just sending two classical bits in our protocol. And for a better twist, the sender even need not know anything about the state that she intends on sending. So, so that is the implication of teleportation. So the implication of this teleportation are pretty clear for secure communication. So somebody is sending in state, they don't know if somebody is trying to tamper with this particular state, uh, that would collapse the state to certain either one of the classical bits, and that will destroy the information of the state. So in that way, the communication protocol is made very secure when we invoke entanglement as a resource for this protocol. Now we'll see how basic quantum mechanics accomplishes this task with ease. All we need is a few gates, a few measurements, and some classical communication. Now, suppose Alice wants to teleport a state psi, a general state like alpha 0 or beta 1, where she doesn't know what alphas and betas are, and her task is to send it to Bob. So the first task that Alice and Bob would do, a priori sending this particular state, is that they would prepare one of the entangled states. Let's say they prepare the first 0 0 plus 1 1 by root 2. That is basically called the EPR pair. So this Hadamard and C naught operation is the one that is essential to prepare this particular state. So upon sharing this EPR pair, they can be depicted as sharing three qubits. Now they have the EPR pair. Now somebody, let's call her Claire. Claire gives the state psi to Alice, and her task is to send it to Bob. So in combination, we have these three lines, meaning we are basically operating with three qubits. First qubit is the particular state that is with Alice, and she intends to send it to Bob. And the second and third qubit is uh, is the part of the EPR pair which both Alice and Bob has. So thus we can explicitly write this composite state at the start of the protocol in this below equation. So we can expand it as on the right hand side. So this is the expansion of the state uh, uh, which we have at the initial stage of the protocol. Now, with that particular state, suppose now Alice applies a C0 operation on her two qubits. So Alice has two qubits, Bob has just one qubit. Bob Bob's one qubit is a part of the EPR pair. Alice's two qubits are one part of the EPR pair as well as the state that the other person has sent to her. So Alice performs a C0 operation with the target state as her EPR pair bit and the control state as the psi state. So she is performing a C0 operation. So when she's like performs C0 operation, this is the form on the right hand side of the first figure. This is the state that we are going to get. Now Alice applies a Hadamard operation on her first qubit, which is the state that she intends to send. So once we apply the Hadamard operation is the one that produces superposition of states. If you apply Hadamard on zero state, you get a plus state, which is 0 plus 1 by root 2. And if you apply Hadamard on one state, get 1, that is, then you essentially get a minus state, that is 0 minus 1 by root 2. So once you operate your Hadamard on the first bit, then this middle equation is the form in which this particular equation morphs to. Now, the most essential uh, uh, trick in the entire teleportation protocol, according to me, is the bottom one. So to once you get the middle state, to analyze the computational basis measurement on the first two qubits, what Alice, or for convenience for us, for our convenience, we group the terms corresponding to each computational basis state for those two qubits. So what I'm trying to say here is that the next set of step would be that Alice perform measurement on her both qubits, and to make it convenient for us to understand, we are trying to do is we're trying to group all the possibilities that she might be getting outside the brackets, such that the third remaining qubit would be mentioned rather in terms of the parenthesis over here. So when she performs the measurement, because it's a two qubit state, she can only get either 0 0, 0 1, 1 0, or 1 1 as the output. And corresponding to each of these outputs, you have these particular qubits, which essentially is the remaining third qubit. So this is the state that matlab, that is this is the particular state, composite states form after all these operations. So I'm rewriting that state in the above line. Now, when Alice would measure her qubits in the computational basis, let's say she gets output 0 0. Uh, of course, that would be with the probability of alpha square by 4 plus beta square by 4. And because we are working with a normalized scheme, alpha square plus beta square is equal to 1. So with 1 by 4 probability, her output would be 0 0. Once she gets the output 0 0, the all the other states are irrelevant here. Only the first state that we see, that is 0 0, in conjunction with alpha 0 plus beta 1, is the state that the system would assume its position in. So once that happens, the resultant conditional state for Bob, why I'm saying conditional, because Alice has actually measured her qubits. She got the outputs in form of 0 0, and this alpha 0 plus beta 1 is the state that remains for the third qubit. And you see, this is indeed the state that Alice was intending to send to Bob. So So you see that by just performing local operations, which Alice performed after the EPR creation, ultimately the quantum mechanical laws are such that either this alpha 0 plus beta 1, or you see in the other possibilities of 0 1 1 0 1 1, which Alice would have got with 1 by 4 probability of each, a version of this particular state psi is the one that Bob would be getting. So the good news is that all these states, psi, x psi, z psi, xz psi, all these operations, x and z based operations, are all reversible operations. So if somebody like Alice, whose intention is to send a qubit state to Bob, sends the information, minimum amount of information to Bob through classical means, that okay Bob, you apply these gates in this particular order, Bob would be able to retrieve the state. So it is very convenient. As for each such case, Bob's state is very similar to original state psi to be teleported, and all Bob has to do is to apply the necessary operations on his part of the qubit. So to complete the protocol, what Alice does is she measures her two qubits on a computation basis, and let's say that the outcomes are z and x. Z being the output she would be getting on her first qubit, and x, let's say, is the output she would be getting on her part of the EPR pair, the initial EPR pair. Each of these z and x are just conventional classical bits. As you see, Alice would be getting either 0001, 10, and 11. So each of these Z and X numbers are just either 0 or 1. So we have these four combinations. What remains is for Alice to send these classical bits to Bob, and she needs to just send two classical bits, and Bob then applies X gate if small x value is 1, and Bob will apply Z gate if the value of Z is 1. And you see in the diagram, this x to the power x and z to the power z essentially says that. So if small x value is 0, then Bob will not apply X gate. And if small z value is 1, he will apply Z gate, and vice versa. And with such gate implementation, Bob actually retrieves the state shy that Alice was tasked to send in the first place. And since the state didn't seem to physically travel between Alice and Bob, you see, there was no classical communication here. Sorry, no quantum communication, quantum channel here. All Alice did was perform the operations on her parts of the two qubits. She just sent two classical bits of information that she could have broadcasted some fax machine or sorry on some internet or on landline phone communication. Some by some classical means she sends these two classical bits to Bob, and Bob then applies certain operators in that particular order which is required, and he retrieves the state. Because there was no physical travel involved, this particular protocol is termed as teleportation. To summarize, the teleportation circuit looks in this particular form. So Alice performs Bell measurement on her two qubits. So after making the EPR pair between Alice and Bob, that is EPA and EPB, she performs this Bell measurements on her two qubits. First a CNOT operation, then a Heidemann operation, and then she performs measurement. Measurement gives her either of these 0001, 10, and 11. She sends these two classical bits to Bob. Bob applies corrective operations I, X, Z, and XZ. And based on that, Bob retrieves the state shy that Alice was intending to send in the first place. So key insights. So quantum state got transferred without having to physically travel. This is the first implication of this teleportation protocol. Classical communication is still necessary though. We send the classical information, but this classical information we could send with confidence that even if somebody makes use of this classical information, repeats this classical information, they don't have that necessary state uh, which could not be copied out from this particular protocol, because no cloning theorem doesn't allow somebody to copy an unknown state. Even they get the information about these two classical bits, they will not be able to make use of this classical bits. So it would be like, so we have no worries about these two classical bits getting replicated and getting used by somebody else. So original qubit got destroyed, and which is consistent with no cloning. So Alice first qubit, which she had, in the process of these gate operations, she actually destroyed that particular state, and it emerged in the third bit, a third qubit, which Bob has the access to, and after certain gate operations, he retrieved that state. So it is consistent with no cloning. So there is only one copy still remaining after the entire protocol starts to ends. So this is a state which this is the kind of protocol which is widely demonstrated in photonic and ion trap experiments. So and its implication in secure communication are pretty clear now. Now let's talk about superdense coding problem. So now the task of Alice is that she wants to send two classical bits to Bob. And to do that, she just wants to make use of using just one qubit. So basically, it sounds like sounds like a sister algorithm or protocol to teleportation, and an inverse protocol to teleportation, I should say. So there, the task in teleportation was that using two classical bits, the task was to send one qubit. Here, with one qubit, we are trying to send in two classical bits. So Okay. To do that classically, because of the classical channel limitations, to send two classical bits, we would indeed need to use two classical bits. We could not do better there. But here, with just one quantum bit, we can indeed perform this kind of operation in which we end up sending two classical bits by sending just one qubit. So we want to see whether how she can perform this uh, using just one qubit, and how entanglement again helps us to achieve this particular protocol. Indeed, entanglement will act as a resource and help us in achieving this particular task. So super dense. Why it's super dense? Because we are sending two classical bits using just one qubit. So the motivation for this is that in classical communication, one bit means we can make use of one bit to send only one bit of information. In quantum communication, we would see that by sending just one qubit and making use of entanglement as a resource, we end up sending two classical bits. So the connection of these things is like it's a dual of quantum teleportation. In teleportation, we send one qubit using two classical bits. In superdense coding, we are doing the inverse of that. We are sending two classical bits using just one qubit. So it's setup and encoding. So again, Alice and Bob will share one of these entangled states. So let's say they start with a state like 00 plus 1 by root 2. They are sharing the first EPR pair, and Alice holds qubit A and Bob holds qubit B. Alice's task is to send two classical bits. So these are out of these four possibilities: 00, 01, 10, and 11. So she intends to send either like one out of these four possibilities to Bob by sending just one qubit. So what Alice does is that she encodes her two classical bits by applying a single qubit operation. So she does this by performing the gate operation on her part of the EPR pair by applying a gate like X, Z, or Y. We basically don't write Y because there is a additional iota factor that gives rise to phase. So to deal with that, we apply X and Z in conjugation, and that has the effect of applying a Y gate without that unnecessary phase term. So what she is doing here, by the way, is that if she wants to send 00, what she will do is that she had this 5 plus, which was 00 plus 1 by root 2. She does nothing with that state, and she just sends this qubit to Bob. Then Bob uh, applies the C0 and Hadamard in this particular order, and when he performs the measurement, he will get the value 00. This is how the protocol works. If she intends to set 01, what she will do is she will just apply X operation or X gate on her part of the qubit. If she intends to send 10, she will just apply Z operation, and if she wants to send 11 to 111 uh, as the two classical bits to Bob, then she will apply X and Z in that particular order. So here from right to left we have to see, because this is okay. So this is the operation from okay, left to right, sorry. So when we write operator Z gate first, time actually in the circuit travels from left to right. So when Z is before X, that means we are operating Z before X. But when we write it mathematically, we have to write in this particular reverse order XZ. That means on the phi state, first ZA operator is acting and then X operator is acting. But on the circuit, it looks inverse. Don't get confused. So then once Alice applies these operations on her part of the qubit, she just sends this particular qubit through a quantum channel to Bob, and Bob then receives this Alice's qubit, and when he receives it, he now uses both of these qubits. He now has this both of these qubits and one of the four Bell states. So to decode this, what Bob does is that he applies these Bell basis measurement using the circuit. So first he applies a C0 operation and then a Hadamard operation on Alice's qubit, and he measures both of these qubit in the computational state. So if the if the uh, qubit which Alice sent, when combined with the original qubit that the Bob had, if it was in the form of 5 plus, when he performs the measurement, he would be getting 0, 0. If it were in a Chi plus state, he would be getting 0, 1. If it was for Phi minus state, he would be getting 1, 0. And in the Chi minus case, he would be getting 1, 1. So that's how this protocol actually works. So Bob's two classical measurement bits are exactly Alice's original 2-bit message that Alice actually intended to send. So here again we have local operation. So what Alice did here is that after making the EPR pair between Alice and Bob can be very distant apart, and now Alice performs whatever measurements, whatever gate operations that she wants to perform. She does it locally. She sends this qubit to Bob. Bob retrieves the state of the Alice. He has now a different EPR pair, a modified EPR pair, and now he does the atom measurement, and the states that he is retrieving as a result has the information about the classical bits that Alice intended to to send. And that is in crux what superdense coding protocol actually is. So the summary and duality with teleportation. So this protocol summary is that resource is again a 1 ebit. So 1 ebit is one equivalent amount of entanglement equivalent of a EPR pair. So that is pre-shared before the protocol actually begins between Alice and Bob. Transmission here is of 1 qubit. In teleportation, we send 2 classical bits. In superdense coding, we are just sending 1 qubit, and the payload, what it results is uh, in Bob retrieving 2 classical bits. So the comparison with teleportation is that teleportation is the protocol in which a quantum state was used to send 2 classical bits. Sorry, when we uh, when we tried to send a quantum state, we made use of 2 classical bits. In superdense coding, we are uh, intending to send 2 classical bits by sending in just 1 qubit and making use of entanglement as a resource. So key takeaway here is that entanglement doubles the classical communication capacity of a single qubit. So, so if we would not have used entanglement as a resource, then there is a theorem by Holivo. He is a scientist. Many years ago, he actually proved it that by sending just 1 qubit, at most you can send just 1 classical bit. Because you see, if you have 1 qubit being sent alpha 0 plus beta 1, a person performs a measurement and he would be able to get only 0 or 1 as a state. So that is equivalent of getting only 1 classical bit. But only because we had entanglement as a resource which was used here, by sending just 1 quantum bit, we could encode the information equivalent of 2 classical bits to be sent to Bob. So entanglement is very essential and acts as a principal resource which actually makes these protocols possible. Again, duality of these protocols. Teleportation is quantum to entanglement plus classical bits. So if you want to send a quantum state, you have to make use of entanglement and classical bits. Superdense coding is, if you want to send in 2 classical bits, you have to make use of entanglement and 1 qubit. Both showcase entanglement as a fundamental communication resource. Its applications and extensions. So the foundation for quantum networks and quantum internet is based on these kind of protocols like superdense coding as well as teleportation. So with this only, people could imagine that we would have quantum networks and quantum internet in the near future. So quantum repeaters also use teleportation. Superdense coding is an efficient information transfer in entangled-based system. So if you want to package your information more efficiently, you would have to make use of superdense coding, and essentially entanglement will act as a resource in that case. Of course, the challenges are there. We still are in NISQ era, that is noisy intermediate scale quantum, in which we have to deal with noise, we have to deal with decoherence and resource management. So these things are of course there. There are fidelity issues because of noises that emerge. But if there were no noise, this protocol actually, in principle, allows us to have these kind of protocols. So, closing an outlook, quantum communication harnesses entanglement beyond classical limits. Uh, Teleportation and superdense coding are like textbook duels of quantum information theory. So, in term, like teleportation and superdense coding are actually inverse of each other, and both of them make use of entanglement as a resource. So, experimental progress is leading towards real world quantum networks, full scale quantum networks, as well as I mentioned before also that protocols like teleportation actually makes it possible for us to implement very difficult kind of gate operations through the process of teleportation. And these are seminal works by a few people, which actually has a lot of applications in quantum error correction. So it is, apart from being idealistic mathematical exercise, it has real world application with regards to quantum error corrections also. Now it's time for quick demonstration on Qniverse. So for that I would be changing my slide. Okay, so okay, I will share this. Okay. So this is our proprietary SDK, which is called Qniverse, in which you can register. Once you log in, you get initially 150 credits worth of points, and uh, on this particular product of ours, we have ready to use several of the algorithms which you can play around with, you can implement for your own use case. So for now, let's say we want to look at quantum teleportation as a thing of interest, and let's say we want to send a state like a zero state, a very simple state, let's say. So this is the kind of circuit that we have, and I will tell you the difference that you will see with regards to what we originally had in the protocol that I just mentioned to you. So you see, the first qubit that is given to Alice is in the form of this zero state, and this Q1 and Q2 are also in your zero state. So the first set of operations that Alice and Bob do is prepare an entangled pair between them. So for that, they make use of Hadamard and C0 operation. I'm using barrier because just want to demarcate them being a separate set of operations. So these are just barrier gates that we are using. They don't do anything. They don't have any disturb. Uh, they don't have any disturbance to the circuit. They just to separate out different sections of the circuit. So the first task was for Alice and Bob to prepare an entangled state. Then came the C0 operation and the Hadamard on the Alice's side of the two qubits. Now, because uh, this involves sending in classical bit of information, so what happens is that we would need a conditional set of gates here, but we don't have those conditional set of gates. If we had conditional set of states here, then depending on the measurement outputs on the first and the second qubit here, Q0 and Q1, we would be applying those relevant operations on Q2 bit, and Bob would be retrieving that. But I encourage you to, because if you use our this Qniverse platform, you will see that each of these operations, for example this one, so when you expand this, Okay. When you expand this, you get the information about the matrices. So, and you can get the information about the matrix form of each of these gates on internet also. So I urge you to just go through the calculations of the implementation of these two gates, and you will indeed see that the state that emerges out of the Q2 qubit is the one that Alice intends to send. So, for example, here, if I do the measurement, uh, you see that we get the states in these form. So, how to read these states? So, the three qubits that are mentioned here have to be read in inverse order. So, the third bit actually is Q0, Q1, and Q2. I hope you understand what I mean by that is the state in the labels in which the states are mentioned here are actually in reverse order. So because Alice, the original intention of Alice was to send a state which was just zero get. So you can see that the the Q2, the first, which correspond to the first bit of the output here, are all zeros. So whenever whatever measurement the pop performs, he is destined to get only zero get. So if I run this operation, let's say I run this operation on a QACC cluster. There are many options to perform this operation on our supercomputer. We can make use of GPUs. We can make use of QPUs also, because that would require a super stack uh, API. So as of now, let's say we are not interested in making use of QPU, but we are running on CPU. I submit this code. You could have changed the name of the circuit that you're implementing here also, and on this side of the panel you can see the circuit ID that is getting that's getting run, and you refresh it, and you see that the state is indeed zero. So I will run it for another state also. So okay, sorry. So now let's say Alice wants to send another state. Let's say she wants to send a state which is a bit skewed. So a state like that would be like, on a statistical ensemble, it would be 30% time it will be 0, 70% time it will be 1. And let's see how the states emerge. So here it's not pretty clear how the connection would come around, but you can see, you can have some sense of what is happening here. There is more probability of the Q2 being in 1 than it is in 0. So it is essentially what we wanted. Let's run this again. Okay, so this is the new circuit ID that got created. So if I run this, so you see, again, it's very close, 709315. So it's very close to what we intended to get. So it's indeed a form of a state like 0.30 and 0.71. So that's how the teleportation protocol actually is performed here. Uh, so now let's look at the another protocol, which is superdense coding. Here what we have to do is we can input the state here, or on the circuit also we can make certain changes, and we can modify our circuit in such a way that we indeed uh, send certain two qubits, the two classical bits that we intend to send. So let's say we want to send 10 state, 10 like classical bits. So for this, the circuit appears like this. Now I'm a bit not happy with this layout of the circuit, because in the uh, original layout of the circuit, we have the operations on Alice's side. So let's say that I'm moving this operation on the Z, on the first qubit itself. I will reverse the order of the first CNOT operation. So I'll make the target state as Q1 and the control thing as the Q0. and I will perform my header mount operation on the first one. So you see, then if I remove this Z part and I just apply nothing, or which is equivalent to applying identity gates, sorry, okay. So when I apply the identity gate, you see that I'm getting with 100% probability the classical bits, the state that Bob is going to get is going to be 0. So what is happening in this circuit, what the barrier means, let me just walk through that. Sorry for not clearing that up. So what happens in the initial stage is that Alice and Bob prepare a EPR pair between them. Then what happens in the second part of the circuit, that Alice performs uh, the desired operation that she wants to perform, so that she can encode those two classical bits in that qubit that she intends to send. And then what happens is that there exists a quantum channel through which Alice sends her qubit to Bob. Once Alice sends the qubit to Bob, now let's say the Bob has both of the qubits and now he has a state, and now he's performing this Bell state creation inverse operation. So in Bell state preparation, you have C naught, he's performing C naught and then Hadamard, and then essentially both the states, both the qubits, he has hold of, and he is making measurements on both of those. So whatever measurement output he would be getting would be he would only be getting, not the Alice. So this is the outcome that he would be getting. So if I replace this I operation with let's say a NOT gate, which is essentially an X gate, you see that now the state is 0 1. As I mentioned, you have to read this in the reverse order. So once you apply your X gate, you are indeed getting a 0 1. If I apply in place of X gate, I apply a Z gate, then we see that we are getting a 1 0 as an output. So Alice did all the operations on her part, sends the qubit to Bob. Bob performs the measurement, and this is the classical uh, complex, like two classical bit of information that he retrieves out of this operation. Now, if he operates Z, okay. So before that, let me show the state vector form. So you see, so here, if this particular state has no phase, that means there is no like phase change. But the moment I apply an X operation here, you see there was a phase change, there is a pi reversal of the phase. So you see, it is very essential to conjugate your gate in a proper order, because if you are not following the proper order, you would be getting unwanted phases. So what I would do is I would reverse the operation, and you see indeed this is the 1 1 classical bit that Bob was originally intending to get. So so with this, I think I will just stop sharing, and I will share my entire window. Okay. So I have demonstrated both those protocol on Qniverse, and I thank you for your attention. So with this, I end my talk.
Thank you, Divyansh.
Yes, sir.
There are few questions. One question by Sumanta Chakraborty.
Yes.
In case of quantum teleportation, is two classical bits after the EPR pair are communicated every time through classical channels, then it is actually classical communication. Is it right?
Okay. So that part in which classical communication is happening, that indeed is classical communication only. But the implication is also important, that through that classical information, we are actually getting the instruction of what gates we have to operate on. Operate our in which sequence we have to operate what kind of gates on our state, so that we retrieve the state. So in that sense, even though the communication is classical, and that also means that we don't worry if somebody tampers with our data. Okay, if they tamper with the data, maybe we would get to know that okay, there is some fault with the protocol. But uh, so so even though it's a classical communication, but it will not affect the veracity of our protocol. Yes.
Okay. Okay. I have few questions after
Yes.
walking through your presentation. I have
Yes.
got few questions. So
Yes.
I heard that you are explaining quantum teleportation is an important resource in quantum communication.
Yes.
Right? Can you explain the reason for that?
Okay. So when I mean that communication, so so indeed communication would not just entail classical information being sent, but also quantum information being sent.
Okay.
Now, the quantum information content is in the state itself. So
Mm.
here, when I'm intending to send a state like shy, which is essentially zero, alpha zero plus beta one, the the information is in that alphas and betas only. Okay, so once I send this state to somebody, that means that I'm sending in quantum information.
Okay.
You see, yeah. So essentially, because I'm sending quantum information, it has clear cut implications in communication protocols.
Okay. And can we send multiple qubit teleportation instead of single qubit?
Yes, indeed, we can do that, and
Okay.
there are works, and indeed, this is something that I have that our team is also working on, and soon we will be having one of the algorithms in which we would be sending in multiple qubit, teleporting multiple qubits rather than just one, which
Oh,
usually many proprietary software out there do. We would be having a product in which we would be sending teleporting multiple qubits. Yes,
yeah, that would be a great work.
yes, yes.
Right?
We are indeed working on that.
And yeah, and what is the importance of bell measurements in both the protocols?
Bell measurement, okay. So you see that in the superdense coding protocol, we indeed perform the bell measurement. So
Mm,
what Alice was doing here was that once Bob actually, like Alice and Bob prepared a EPR pair between them, and Bob went a bit of a distance away. Then
mm,
Alice actually did local operations on her part of the qubit. So once she did that, she essentially changed the EPR state from one basis state to the other basis state. And then when she sent the her part of the qubit to Bob, then essentially sending that particular basis. So the composite state that Bob will get after retrieving the qubit from Alice would be some another Bell state. So that indeed is a Bell measurement only, because when he will perform the measurement on both those qubits, that would come down to sorry.
okay, okay.
Okay.
Uh, there is one question by Chitra.
Yes.
In teleportation, Bob measures the state based on Alice message.
Yes.
Will he does measurement with respect to all Bell states or only based on the Alice information?
Only on the basis of Alice information. If he does any other operation, then he would not be able to retrieve the state that was intended to be retrieved. Yes.
Okay,
Yes.
yeah.
Yeah.
And how can we integrate this in existing classical communication?
Okay, so the goal of teleportation is to actually transfer a quantum state, right? So,
Hmm.
so classical communication is a part of this teleportation scheme. So, when we are saying that local operation, classical communication, basically, so here classical communication becomes just a part of teleportation. So, in that way, it has to be integrated. Yes.
Okay.
Yes.
Yeah, I think there is one question
Yes.
asking for the email address. So, Ms.
Okay.
Nalini, you can write to qniverse@cdac.in.
Yes. Yes.
Yeah,
And my email ID, if they want, it's just divyansh@cdac.in.
yes.
Yes.
Uh, yeah, with this, I think we have come to the. Oh, there is one more question.
Sure.
Vinayaka K. PM.
Yes.
If someone If someone in gets that classical communication information, they can actually decode the qubit information, right?
No, they
Quantum,
cannot. They cannot.
they cannot.
They
Okay.
cannot. Why is that the case? Because that that qubit, that Q2 that I mentioned, which Bob actually had, right?
Hmm.
So that was always with Bob.
Okay.
In the wires, it looks like that something is actually traveling, but that is not the case. Those wires just mean, okay, there is a time direction involved. From left to right, we have to see. But that Q2 bit was always with Bob. Nobody
Okay.
else has. So even if they retrieve the classical bits that Alice is sending, they cannot do anything with that because they don't have the qubit on which they will have to do the manipulative qubit gate operations, right?
Mm,
So yeah, so in that case, it's okay. It's safe. Yeah.
yes. Uh, yeah.
Anything else?
I think that's all. Yeah.
Okay.
Thank you, Divyansh,
Thank
and
you.
thanks for all the participants for joining. Uh, hope we see you next time, next
Yeah.
week.
Thank you for giving me the opportunity,
Th-
sir.
yeah.
Okay.
Thank you.